Thank you everyone for joining us and welcome to the Cancer Research Institute's webinar series, Breakthroughs in Cancer Immunotherapy. Today's date is Tuesday, October 21st, 2014, and today's webinar is titled Breast Cancer, the Latest Target for Immunotherapy. My name is Brian Brewer and I'm Director of Marketing and Communications at the Cancer Research Institute. Cancer Research Institute is the world's only nonprofit organization dedicated exclusively to harnessing the immune system's power to conquer all cancers. We fund scientists globally whose work has led to significant breakthroughs in treating cancer with immunotherapy. Over the next 45 minutes, you'll have an opportunity to hear firsthand from an expert in the field how the treatment of breast cancer today is undergoing a revolution thanks to these breakthroughs. After a 25-minute presentation from our speaker, we will open the discussion to questions submitted by you. You can pose your questions at any time throughout the webinar by typing in the Q&A box on your screen. Today's webinar is being recorded and will be made available for viewing on the Cancer Research Institute website and our YouTube channel. Now, it's my pleasure to introduce our speaker. Dr. Leisha Emens is an associate professor at the Sidney Kimmel Comprehensive Cancer Center at the Johns Hopkins University School of Medicine. She's a medical oncologist who specializes in breast cancer care and is a member of both the Cancer Immunology and Women's Cancer programs. Her research focus is developing innovative immune-based therapies that incorporate cancer vaccines, standard cancer drugs, and immune checkpoint inhibitors as treatments for breast cancer and gynecologic malignancies. We are honored and delighted that you could join us for today's webinar, which is being held during Breast Cancer Awareness Month. Dr. Emens, welcome.
Thank you so much for the invitation to participate. So it's really a pleasure to be here today and discuss with you some of the latest advances in immunotherapy for breast cancer. It's really an exciting time for immunotherapy as a field and for breast cancer in particular, as I think there's newfound appreciation for the role of the immune system in breast cancer prognosis and treatment. This slide just shows the conflict of interest statements that I'm required to make. It includes a licensing agreement between our institution investigators and Aduro for the vaccine that I'll discuss a little bit about, research funding from Genentech and Roche, as well as EMD Serono actually, and then I've given advice to several other companies. I'll discuss off-label and investigational use for several drugs, including marcotuxomab and CDX-011, which are investigational tumor-specific monoclonal antibody-based drugs, 2 vaccines, Newbacks and breast cancer GBacks, as well as several checkpoint agents specific for CTLA-4, PD1, and PDL1. Of those, ipilimumab or Yervoy and pembrolizumab or Keytruda are both approved for melanoma, but at this point for no other cancers. So this slide summarizes what we'll cover in the talk. First, we'll just briefly review breast cancer as a fairly complex type of cancer. And then I'll turn my attention to the different types of breast cancer immunotherapy. The first has been in use for quite some time, and that is tumor-specific monoclonal antibodies, including trastuzumab and pertuzumab, antibody drug conjugates like TDM1, which is trastuzumab-based, and a novel one called CDX-011, and marcotuxomab. I'll then talk a little bit about T-cells as the target of immunotherapy strategies and the main effector of the immune response against cancer. Discuss 2 vaccines, nelipepimut S, which is a HER2 peptide vaccine, E75, that's used with GM-CSF as an adjuvant. That's Newbacks, as well as GM-CSF secreting breast tumor cells, which is GBacks. I'll talk briefly about immune checkpoint blockade, both agents targeting anti-CTLA-4 as well as anti-PD1 or anti-PDL1, and then conclude talking a little bit about the major points of the talk and the future of breast cancer immunotherapy. So first, just to review breast cancer, it's actually a complex collection of diseases with heterogeneous biology and clinical behavior. If you look genomically at these tumors, they can be broadly divided into luminal A and luminal B subtypes, a HER2-enriched subtype, and a basal-like subtype, which tends to be triple negative. The poor man's way to subdivide these, aside from genomics, is by immunohistochemistry. Luminal A is ER and PR positive, but HER2 negative. The proliferative rate as measured by Ki-67 is low, and it is responsive to endocrine therapy. That's the targeted therapy we use for luminal A cancers. Luminal B cancers are ER and or PR positive and can be either HER2 positive or negative. They have a tendency to be more aggressive with a higher proliferative rate. Agents that we can use to treat this type of breast cancer include endocrine therapy, HER2 targeted therapies, as well as chemotherapy. HER2 enriched breast cancers are ER negative and PR negative officially, and HER2 overexpressing or HER2 positive. And we use HER2 based therapies in conjunction with chemotherapy for those. And then finally, basal-like breast cancers, which are triple negative and do not express any of the established targets for breast cancer. We are only able to use chemotherapy for basal-like or triple negative breast cancers at this time, as there are currently no targeted therapy options for this disease type, and it remains a major unmet clinical need. So the whole purpose of the immune system is self-non-self discrimination, or to be able to detect what is you from what is not you. And by doing so, the immune system is designed to discriminate threats from basically a stable situation. So first, there's non-self discrimination to avoid self-destruction, which comes about through autoimmune disease, where the immune system becomes activated to react to your own tissues. That's diseases like lupus or rheumatoid arthritis. And then it protects against threats. So protects against exogenous infectious invaders like bacteria or viruses, as well as endogenous threats such as cancers, which are a form of dysregulated self. If you think about this, cancers arise from your own tissues, so your immune system has a tendency to view cancers as a form of self. That is why it's difficult for the immune system to see cancer sometimes, and also why, not surprisingly, with effective immunotherapies, the side effect profile that you see is consistent with autoimmune type diseases. It's really kind of the flip side of the same process. So we'll first talk a little bit about tumor-specific monoclonal antibodies, which have really transformed the therapy of HER2-positive breast cancer. These breast cancers were historically quite aggressive and had shorter survival than breast cancers that did not overexpress HER2. The development of trastuzumab or Herceptin and the subsequent development of pertuzumab or Perjeta, Omnitarg is the older name for that, really transformed the treatment of these breast cancers. Trastuzumab was one of the first drugs to really show an overall survival benefit for metastatic disease. It's a monoclonal antibody specific for HER2 homodimers and binds to the protein here at this point and inhibits signaling through the cell. When combined with chemotherapy for metastatic disease, it has a modest improvement in overall survival, and actually for early stage breast cancer decreases the risk of relapse by 50% or more. Pertuzumab is a drug that's also specific for HER2. It binds to a different part of the molecule and prevents dimerization of the HER2 molecule with other members of the HER2 family, such as HER3. It's recently been tested in combination with trastuzumab, and I'll show you some of that data in just a moment. Marcotuxomab is a novel HER2-specific antibody that I'll show you a little bit of data for that's in development actually for breast cancers currently that do not overexpress HER2. So this is the Cleopatra study design and is the most recent advance in the use of HER2-specific monoclonal antibodies to manage HER2-positive metastatic breast cancer. An update on the survival analysis was just presented at ESMO this past month. It enrolled 808 HER2-positive metastatic breast cancer patients and randomized them to receive standard Herceptin-based chemotherapy with trastuzumab combined with docetaxel, or the investigational combination of trastuzumab with pertuzumab and docetaxel. This is the final overall survival analysis that was just released at ESMO, and with a median follow-up of about 15 months, there was nearly a 16-month improvement in overall survival with the addition of pertuzumab to trastuzumab-based docetaxel therapy, which is really unprecedented for stage 4 HER2-positive breast cancer. The p-value was highly significant here, and this is currently the standard of care at first-line therapy for metastatic HER2-positive breast cancer. So once someone has progressed through the standard HER2-specific therapies, there is, or the standard HER2-specific antibodies, there are other drugs that can come into play. Trastuzumab Entancing, or TDM1, this is Kadcyla. It provides proof of principle for antibody drug conjugates, which is a strategy where you take the tumor-specific antibody and connect the chemotherapeutic agent or toxin directly to the antibody through the use of a linker. This enables the drug to be delivered directly to the tumor, thereby increasing the precision of therapy and decreasing the side effects. Trastuzumab Entancing is the first example of this. This is data from the seminal trial for this, which was tested in patients who'd previously had trastuzumab and a taxane. These are patients with advanced HER2-positive breast cancer that were randomized to receive standard therapy with lapatinib and capecitabine, or the new agent TDM1 or trastuzumab Entancing. And you can see that the antibody drug conjugate gave a better progression-free survival, increasing survival from 6.4 to 9.6 months, as shown here. And this again was statistically significant in a good way with a p-value of less than 0.001. So as I had mentioned, triple-negative breast cancers or basal-like breast cancers really are without a target for therapy at this point. And given the proof of principle for trastuzumab Entancing, there are other antibody drug conjugates under development. One of them is promising for triple-negative breast cancer, and this is CDX-011 or glambatumumab vedotin. This is a monoclonal antibody specific for the glycoprotein NMB or GPNMB. It's conjugated to the toxin MMAE. There was a randomized phase 2 study of this agent versus investigator's choice chemotherapy in advanced GPNMB overexpressing breast cancer. The drug was very well tolerated, with the most common adverse events being rash and neuropathy. The overall response rate was 33% in patients with triple-negative breast cancer and/or tumors that expressed GPNMB at high levels. The median overall survival was 10 months for patients treated with this novel agent, compared to 5.5 months for patients who received standard chemotherapy. And this was statistically significant with a p-value of 0.003. There's currently a phase 3 pivotal trial of this agent, randomizing patients to CDX-011 or Xeloda for advanced GPNMB overexpressing triple-negative breast cancers that is currently accruing patients. Now, with that as an introduction to immunotherapy with the use of agents that directly target the tumor itself, the other approach to immunotherapy is to engage the immune system in other ways. And in order to start thinking about this, I just wanted to take a moment to review the two major functional arms that comprise the immune system. The first general category of immunity is innate immunity. Innate immunity serves as the first line of defense to protect the body. It serves a sensing function, and the cells that subserve this are cells like macrophages, monocytes, dendritic cells, and natural killer cells, as well as various soluble factors. The second major category of immunity is adaptive immunity. This is antigen-specific rather than non-specific, and it serves a highly targeted protection and threat elimination function. The cells that subserve this purpose are T cells, particularly CD4 positive helper T cells and CD8 positive killer T cells, as well as a regulatory T cell that's CD4 positive and FOXP3 positive. These act to counterbalance the activity of effector CD8 positive T cells, and then B cells, which differentiate into plasma cells and secrete soluble antibodies. Bringing this full circle, the antibodies can then interact with macrophages or natural killer cells to link the adaptive and innate immune systems in an antigen-specific way, thus ensuring a well-orchestrated response to either an exogenous threat or a developing tumor. So with that as an introduction, we'll just talk briefly about marcotuxomab, or MGA-H22. This is a monoclonal antibody that is Fc enhanced or genetically engineered. It's derived from the parent antibody of trastuzumab that's specific for HER2 and binds to the same epitope with very high affinity. At the other end of the antibody molecule, which interacts with NK cells and macrophages, there were modifications made to the constant domain to enhance its ability to interact with NK cells, as well as monocytes and macrophages, and recruit those innate immune effectors into the tumor microenvironment. This slide summarizes some of the clinical data from the phase 1 study of marcotuxomab, and this just shows you a waterfall plot of patients with breast cancer, gastroesophageal cancer, or other cancers that were enrolled into this study and received different doses of the drug, is shown in the color coding at the bottom of the slide. Uh, the bars that rise above the horizontal line are patients who progressed on the therapy. Once you get to this point and the bars go below the horizontal line, these are patients who responded to the therapy. And you can see out here that there are 3 patients with breast cancer that responded relatively well to this novel monoclonal antibody. As a result, there's currently a single-arm phase 2 study testing this FC-optimized HER2-specific antibody for breast cancer. And these are patients who are not eligible for standard HER2-directed therapy. They have relapsed or refractory breast cancer that's considered HER2 negative by standard criteria. And by that, I mean HER2 expression levels at 2 plus by immunohistochemistry, or FISH non-amplified with a HER2 gene that's non-amplified. These are patients that would not normally be treated with trastuzumab or other HER2 targeted therapies. And as I said, this is now ongoing. So now we'll switch our attention to T-cell mediated immunity or adaptive immunity in breast cancer. And it's clear now that breast cancer can induce an adaptive immune response. And this is illustrated here on the left part of the slide that just shows you a resected breast tumor where total CD3 positive T cells were stained. That's the brown staining. And you can see that they're really attracted to the tumor and essentially primarily are retained in the periphery of the tumor. There's a few scattered cells within the interior, but they really ring the tumor around the exterior stromal areas. And this again is an untreated breast cancer. On the right part of the slide is work from my colleague Sandra DeMaria, who was one of the first to show that standard breast cancer therapies can promote T-cell immunity. The middle panel shows a newly diagnosed breast cancer prior to therapy. This patient was given neoadjuvant paclitaxel or the infusion of paclitaxel prior to breast surgery itself. And you can see that this drug induced the infiltration of a very brisk infiltrate of T cells into the tumor, so that the use of paclitaxel actually promoted the entry of T cells into this cancer. These findings imply that we can harness the immune system in order to treat breast cancer. There is very rapidly accumulating data that both CD8 positive effector T cells as well as regulatory T cells impact survival in breast cancer. On the left panel is illustrated the impact of stromal CD8 positive T cells, which confer a good prognosis, where CD8 in T cell enriched tumors do much better in terms of their breast cancer survival, as shown in blue, relative to the CD8 poor breast cancers. On the right side of the slide shows you the influence of regulatory T cells that overexpress the transcription factor FOXP3. And you can see primary breast tumors that have fewer of these bad T cells do better than primary breast cancers that have a brisker infiltrate of these bad T cells. So both of these types of T cells can impact breast cancer survival. This is neoadjuvant data that shows you that a favorable balance of CD8 positive effector T cells relative to Tregs can predict survival, and also shows you the impact of therapy on this balance. These are patients, again, who were diagnosed and their tumor microenvironment was analyzed prior to treatment. And you can see that patients who had either a favorable CD8 positive to FOXP3 ratio or an unfavorable had about the same outcome. After treatment, if a more favorable CD8 positive effector T cell to Treg ratio was induced, the patients did much better in terms of their survival. So, as I mentioned, the presence of T cells implies that we can activate these T cells in order to improve outcomes in breast cancer. And this is just a slide that illustrates Newbacks, which is the E75 HER2 peptide vaccine given with GM-CSF as an adjuvant. And this is data from the early trials of this vaccine. And it's given after primary therapy for breast cancer, where patients have had all of their standard breast cancer therapy. And this vaccine is used as an extra insurance policy much the way bone marrow transplant used to be used in order to prevent relapse. This shows the impact of the vaccine on the relapse rate for all patients. And there was a very small improvement in the relapse rate. This focuses on patients who expressed low levels of HER2, where the numbers were somewhat smaller than the panel on the right side, but the impact of the vaccine was greater. As a result of this data, there's currently a phase 3 trial called the PRESENT trial that's underway for high-risk, early-stage breast cancers that do not overexpress HER2, where this vaccine is being utilized in order to see if it can meaningfully impact the relapse rate in those patients. So, assuming that we have T cells that can potentially recognize breast cancers, is that enough? And really, it's probably not. And this slide just illustrates how T cells typically see tumors. For effective T cell activation, two signals are generally required. The first is subserved by the presentation of an antigen, as shown by this blue dot, in the context of self, in this case, an MHC molecule. And tumor cells can present self antigens in the context of MHC, which is recognized by the T cell receptor present on a specific T cell for that antigen. This confers signal 1 to the T cell. What tumor cells are typically unable to do is present a co-stimulatory signal, or signal 2, to complete the activation sequence for T cell activation. And in the absence of a second signal for T cell activation, T cells are typically shut off and the immune response is aborted. So the GBacks vaccine platform really focuses on restoring signal 2 in order to effectively activate tumor immunity. And this is based on the concept of genetically modifying tumor cells, for example, a breast tumor cell, to secrete a cytokine called GM-CSF. That's represented by these yellow dots here. The tumor cells are injected after irradiation to ensure that they cannot grow underneath the skin, which is rich in these professional antigen presenting cells or dendritic cells. These are cells that are specially programmed to activate immunity and can present antigen as well as provide the all-important signal 2. These cells act like the orchestra leader for the immune system and basically tell what parts of the immune system to become active and what parts to be quiet in order to get the most effective immune response. They are attracted to the site of the vaccine cells, and as the vaccine cells break apart, these dendritic cells engulf and take up bits of the tumor cells, break them down into these antigens and present them in the context of self, also present signal 2 so that the T cells are effectively activated, as shown here, and expand and can then traffic and migrate to the area where the tumor cells are, regardless of where that could be in the body. So that's how we think the GBacks vaccine could work. And it's even more complicated than restoring signal 2, and it turns out that that's probably not enough either. And we found this by looking at a preclinical model of HER2-positive breast cancer. On the right part of this slide over here, we're utilizing a mouse that's transgenic for rat HER2. So these mice express the rat HER2 protein under control of a regulatory sequence that drives its expression specifically in breast tissue. As a result, they get spontaneous breast cancers that look just like human breast cancers. We derived a cell line that we can grow in the lab in dishes from the breast cancers of these mice so that we can challenge mice in experiments with that HER2 positive cancer. The parental mice, as shown over here, are the mouse line that these HER2 mice were derived from, and they are genetically identical to the HER2 or new transgenic mice, except for they don't have rat HER2 in their germline DNA. As a result, the immune system of the parental FEBN mice recognize HER2 like an infection. In this mouse model, the control vaccine is a fibroblast cell line that secretes only GM-CSF and does not deliver the antigen, so it's HER2 negative. The specific vaccine secretes GM-CSF and delivers HER2. So you can compare the response of these parental mice, which recognize HER2 as an infection, to these transgenic mice, which recognize HER2 as self, and more faithfully recapitulates the situation in patients. And you can see that if you let the tumor grow to a fairly big size in these non-tolerant mice, and then vaccinate with a control vaccine, the tumors continue to grow out. If you give the HER2 targeted vaccine that makes GM-CSF, the tumors initially stabilize in size and actually begin to shrink. And we can actually cure 100% of these mice of pre-existing tumors because these mice, as I mentioned several times, recognize HER2 as foreign, like an infection. In stark contrast, these mice really do not respond to the specifically targeted vaccine at all, even when the tumors are very small. And you can see that these tumor outgrowth curves completely overlap, showing the complete lack of effectiveness of the vaccine in the HER2 transgenic mice, where the immune system sees rat HER2 as self. So we theorized that we could combine the vaccine with other agents to separate these curves out, improve the immune response induced by the vaccine to try to achieve this over here. That is our goal. And the first thing that we tested in this regard was adding therapeutic HER2-specific monoclonal antibodies in low doses of cyclophosphamide. And this is an experiment that shows that we can separate these curves out by using the strategy in the HER2 transgenic mice. Again, the open circles show that all the mice come down with tumor very quickly in mice that only receive the vaccine. In the open squares, if you add low-dose cyclophosphamide, and what that does is gets rid of those bad Tregs. If you add that to the vaccine, you delay somewhat, and you can actually cure, but only about 5 to 10% of the mice. If you add the HER2-specific monoclonal antibody, 716-4, to the vaccine, you get a better delay and cure more of the mice. If you add all three agents together, you get the best delay, and you can cure upwards of 55 to 60% of these mice. If we look at the HER2-specific CD8 positive T cells that are induced with this approach, you can see that there's a very weak induction with vaccine alone. It's enhanced to about the same levels by adding the antibody or cyclophosphamide, but if you add all three together, you get by far the greatest number of T cells, and this is consistent with the best improvement in overall survival that we saw over here. Now, we've tested a human GM-CSF secreting breast cancer vaccine that delivers multiple proteins, including HER2, in patients in combination with chemotherapy alone or both chemotherapy and Herceptin. And this just shows the T cell responses specific for HER2 that secrete gamma interferon or TNF alpha to cytokines that are indicative of good T cell activity. And it shows you the impact of cyclophosphamide and Herceptin on the levels of these T cells. And you can see here that the vaccine by itself in the solid line induced a very low number of T cells. Adding cyclophosphamide the day before to get rid of those regulatory T cells improved the level of the T cell response, but really adding Herceptin to the vaccine gave the best levels of T cells, both that secrete gamma interferon and TNF alpha. This is two different trials, so it's not the most fair comparison, but I think it does illustrate the concept that hitting multiple points of immune regulation can improve the vaccine-induced T cell response. So this just is included to illustrate the concept that signal 2 is not a simple signal. It's really a rheostat that allows the strength of T cell activation to be dialed up or dialed back. Again, just to remind you, signal 1 is antigen specific. It's recognized by the T cell receptor, recognizes antigen in the context of MHC or self. Signal 2, the positive signals subserved by B7 binding to CD28. And it's counter-regulated by CTLA-4. CTLA-4 is the target of ipilimumab. It turns out that there is an array of other signals that also come in to make up signal 2. PD1 and PDL1 is the pathway that is under the most intensive investigation at this point, but there are others. And it's actually the sum of these levels of both positive and negative activation that determine the ultimate strength of the second signal. So you can really control the strength of T cell activation by manipulating this very complex system of signaling between the T cell and the antigen presenting cell. So these molecules identified as immune checkpoints, as I mentioned, are major points of T cell control and also represent potent therapeutic targets. And this is just a blow up of the immunologic synapse, or that complex of interactions between the dendritic cell and the T cell, or the T cell and the tumor. And again, illustrates signal 1 with a positive signal 2 conferred by B7 and CD28, and the negative signal by CTLA-4, which can be blocked by a monoclonal antibody specific for CTLA-4. You get rid of this negative signal and allow effective T cell activation to proceed. At the effector phase at the tumor site, this negative signal can be mediated by the engagement of PD1 on the T cell with its ligand PDL1 on the tumor. And there are multiple drugs that are specific for either PD1 or PDL1 that are antibody-based that are under active investigation. Pembrolizumab has been approved by the FDA for melanoma. There are a variety of others that are under active investigation for a number of different types of cancer with evidence of fairly impressive activity. This is an example of the clinical activity of anti-PD1 monoclonal antibody therapy in melanoma. It shows you the ability of melanoma patients to respond to this therapy early on with objective responses. One of the things that's astonishing about these drugs is that after the immediate objective response, the tumors occasionally stabilizes and the responses are actually quite durable, with the responses lasting weeks to months to even years. It appears that PD-L1 expression by the tumor can enrich for the likelihood that a patient will respond to therapies targeting either PD-1 or PD-L1, and that patients that are PD-L1 negative typically don't respond, but some patients who are PD-L1 positive appear to respond. Not all do, and actually some emerging data suggests that PD-L1 negative patients can also respond. So this is a very complicated area, and we'll need to watch the progress in the use of PD-L1 as a predictive marker of response to these therapies very closely. So breast cancers can express PD-L1 on the tumor cell surface, and you can see that as this ringed staining on the tumor cells. And this suggests that breast cancers could respond to targeting the PD-1 pathway. There are a number of reports looking at PD-L1 or PD-1 expression in breast tumors. Generally, this is associated with worse prognosis in untreated tumors, but there is at least one report to suggest that PD-L1 expression at the mRNA level, the non-protein level, could be associated with a better prognosis. And again, we'll have to see how all that plays out. And we'll have the first report of the clinical activity of two agents that target the PD-1 pathway, MPDL3280A, as well as pembrolizumab, in triple-negative breast cancer in December at the San Antonio Breast Cancer Symposium. So we'll wait for that data to be described. So in conclusion, what I've tried to show you today is that breast cancer can be immunogenic, as well as breast cancer therapies. Standard cancer therapies can promote tumor immunity and support tumor immunity. Breast cancer vaccines are promising, particularly if you use them in combinations that engage different parts of the immune system. And immune checkpoint blockade is emerging as a viable immunotherapy strategy for breast cancer. And I think the future really lies in combination immunotherapy strategies, which include accelerating immunity with vaccines, which is like stepping your foot on the gas of the immune system, relieving the brakes on the immune system with immune checkpoint blockade and other strategies, and then finally supporting immunity with the optimal integration of standard cancer drugs that may include tumor-specific monoclonal antibodies and or chemotherapy. And with that, I think we can take questions.
All right. Thank you so much, Doctor. That was quite illuminating. We do have some questions that folks who are watching have posed. You can continue to ask your questions at any time by typing in the Q&A box. We'll try to get to all the questions that we can. Dr. Emens, the first question I'll take is a couple people actually asked this, and I think this is a common question we get in these webinars and when we're out talking to patients about immunotherapy and the immune system. And the question is, what can a patient do? What can an ordinary person do? Are there vitamins? Are there nutritions? Or are there things that this person can do to improve their immune system when it comes to cancer? So we've answered that question a lot of times, but I'd love to hear what your answer to that is.
So that's a great question, actually. And usually what I tell people is to make sure they eat a healthy, well-balanced diet with, a quarter of the plate representing good quality protein, a quarter representing starch, and the rest of it representing fruits and vegetables, hopefully more vegetables than fruits that really represent the full spectrum of the rainbow. That lets you get good nutrients in through foods that are directly from the earth, which is a healthy way to be. Good exercise, so make sure you get good exercise, and then sleep is really important. I'm not aware of anything specific per se that you can do to really amp up your immune system other than take the best care of yourself. Manage your stress, so meditation. So I'm a big proponent of all of those things that just will promote a healthy lifestyle in general.
All right, thank you for that. Um, Someone else just asked about breast cancer stem cells and wondering whether immunotherapy works differently on them than other types of breast cancer cells. So could you first explain to us what a breast cancer stem cell is and then answer the question?
So that's a really excellent question. So there's a theory that not just breast cancer, but many cancers have stem cells that really serve as the locus whereby tumor cells renew their ability to proliferate. So it's thought to be perhaps a reason why tumors can persist even after there's been a good response to therapy. It's thought that stem cells are sometimes left behind. And actually, it's very attractive to think about the immune system as a way to mop up those stem cells. I think there are some examples of antigens that may be more selectively expressed on stem cells than are not. Even if there are not, you can induce an immune response to shared antigens that may provide a mechanism distinct from chemotherapy that will circumvent the chemotherapy resistance that's thought to be typical of stem cells and actually eliminate them. So that's one of the potential ways that immunotherapy and chemotherapy could complement each other.
Yeah, I was very interested in your slides on that. That is an area of focus here at Cancer Research Institute going forward as we learn more about the immune system and how to trigger it to detect and eliminate cancer. We're very interested in seeing how that will overlap with conventional therapies
Yeah.
like chemotherapy. All right, let's see. Is PD-L1 upregulated in breast cancer patients? So you did talk about PD-1 expression in breast cancer, but let's just revisit it quickly. And can you explain what is upregulation?
So upregulation means the change in expression from a given level to a higher level. Generally speaking, it can occur by a variety of mechanisms. PD-L1 is a complicated marker, so it's a dynamic biomarker, unlike something like um, a fixed gene mutation, which is not dynamic and typically doesn't change as readily as something like PD-L1, which can be induced. It's thought that one mechanisms by which tumors resist the efforts of T cells to attack them is that when T cells traffic to the tumor and release gamma interferon, PD-L1 is upregulated by the tumor cells as a mechanism of escape, so that the actual immune response itself can upregulate PD-L1 expression on the tumor cells and provide a means by which the tumor cells can resist the T cells. That's one of the reasons why blocking that pathway is particularly attractive if the T cells are already there.
Okay, thank you. Um, so we've seen in your slides that some immunotherapies and certainly the combination approaches are able to produce statistically significant benefit in patients, and then certainly, of course, in the laboratory models that you showed us. So the question is, since cancer is such a tricky little monster in terms of its ability to mutate and adapt to its environment for its own survival, what happens later on? Let's say someone receives a vaccine or a checkpoint blockade, and then years go on. What's the risk of that cancer coming back?
Well, the beautiful thing about the immune system is its ability to recognize multiple different antigens, and really it's unlimited. So the immune system has the capacity to, um, you can get something called epitope spreading, where if you target one antigen expressed by a tumor and you lyse that tumor, you get the release of other antigens that the immune system can then become educated to recognize. So the immune response can adapt to the tumor and adapt to the tumor as it changes. The key is just keeping that immune response active.
So it's almost like a ricochet effect. You're aiming your ball at one target, but through destroying that target, you're releasing other targets to the immune system.
That's exactly right.
So this is actually a very good question. When a patient is first diagnosed with breast cancer and is about to undergo, in the case of a patient who can be treated surgically, or even in patients who can't be treated surgically, are there particular tests that a patient should ask related to the immunogenicity of her breast cancer, or in case of male breast cancer, his. And if these tests aren't available, how should the tumor tissue be preserved for later tests?
So there is not any standard testing that we would base any clinical decision making on in terms of newly diagnosed breast cancer. So we don't routinely assess breast cancers for T cell infiltration or FOXP3 T cell infiltration. We don't routinely assess them for PD-L1 expression. That could change in the future, but at this point, it is not part of the standard of care. That's an area of evolving and increasing interest, is to really get a better grasp on the immunologic phenotype of cancers and how it relates to survival. And I think it will be important to do that as more immunotherapies become available. With regard to the future, let's say you're diagnosed with breast cancer today and your tumor is removed surgically. Typically, we can go back to the preserved tumor, and there are ways to test an archived tumor for expression of given immunologic molecules or even for T cells. For example, we're doing studies now on tumors that were diagnosed as much as 5 years ago. With the PD-L1 studies and the PD-1 studies that are done now, we sometimes get archival tumor to test for PD-1 or PD-L1 expression, typically PD-L1 expression. Occasionally, we do a fresh biopsy if the archival tumor is too old, but you can go back to older tissue to test some of these things.
Okay. For triple negative breast cancer and anti-PD-L1 therapy, how should we think about identifying likely responders? Is it PD-L1 expression plus baseline tumor infiltrating lymphocytes, or instead is it more dependent on lack of AR or other? I'm not sure what AR is, are you?
Yeah, so AR is androgen receptor. So I think we don't know exactly what the best predictive assays are. It's an area of intense investigation. Every company testing these agents in the different cancer types have their own assay that they're co-developing along with their drug. So I think it's an open question. What people seem to be focused on right now is PD-L1 expression, either by tumor cells or by lymphocytes within the tumor. But as I said, it's an open question, and a lot more research is required to really know what the best predictive biomarker is going to be.
Okay, we've got time for just one more question. Do you envision the day when one could get a breast cancer vaccine or any other type of cancer vaccine as a preventive strategy?
I do envision the day. So I think the first step for that is the setting, much like the present trial, where people have had their initial diagnosis and their initial treatment, and the vaccine is given to prevent relapse. That's called secondary prevention. Once proof of principle is shown in that setting, it certainly is very simple to imagine taking a fairly straightforward vaccine like a peptide vaccine into the prevention setting. Those trials are harder to do because the outcome is so far down the road, so they take a lot of time. But I certainly can envision a day when we'll have an effective vaccine for breast cancer prevention, and there is a lot of interest in making that happen as soon as possible.
That's fantastic. But it is great now to see effective strategies for therapy. So that's good. So I'd like to thank everyone who submitted questions. I'm sorry that we can't get to them all, but it is wonderful to see such interest from all of you in Dr. Emens' work and in the field of immunotherapy for breast cancer. So we're going to wrap up. If you'd like to watch this webinar again or any of our other previous webinars, you can do so at cancerresearch.org/webinars. I'd also like to let you know that we do have a website that we launched earlier this year called theanswertocancer.org. It's specifically for patients and for caregivers. So for those of you interested in learning more about the clinical trials that Dr. Emens spoke about, or if you'd like to learn more about other clinical trials for breast cancer or other cancers, you can go to theanswertocancer.org. We have a clinical trial finder service available there. Someone can help you find a trial that for which you or a loved one may be eligible. Also, for those of you in the New York region or willing to travel to the New York region, next June we will be having our first 2-day, 150-mile bike ride to raise funds for the Cancer Research Institute, specifically for immunotherapy research in cancer. You can learn more about this exciting epic event at ridetovictory.org/New York. I hope to see you on the road. I'm the team captain, and I'm really looking forward to it. And that concludes today's webinar. Thank you again so much, Dr. Emens. Thank you, everyone, for participating, and we look forward to next webinar. Bye-bye.
Bye.